Okay, so good afternoon, everyone. Welcome to this edition of our October, October. We are in October. Sorry, the edition of our NITheCS Mini-School. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS. Today, it's a real great pleasure to introduce the two speakers, Professor Amartya Goswami and Professor Zurab Janelidze. Amartya is based at the University of Johannesburg and Zurab is based at the University of Stellenbosch. Yeah? And just a week or two ago, we met at a virtual social event. Yeah, we never met before. Yeah, and in the discussion, I told them that because of my interaction with my PhD supervisor, Professor Josef Honerkamp, who is also in the audience today, I got interested in learning a little bit about category theory because we tried to learn it together. Yeah, and Amartya and Zurab immediately offered to give us an introductory course to category theory. And this is really nice because, as you know, NITheCS is now no longer concerned only about theoretical physics, but it also takes care, among other disciplines, of mathematics. So this is our first ever mathematics training event. And I know that Amartya and Zurab has prepared something very special. So it will probably set the standards for the future. Yeah. So Amartya and Zurab, people are not here to listen to me. They are here to learn about category theory so that they hopefully can also start using it. If you would like to start, you're most welcome. Sorry, one thing I've forgotten. To the participant, please make use of the Q&A facility at the bottom of the Zoom screen to ask questions. And maybe if it's really important, just raise your hand and we'll make an effort to give you the right to speak. Yeah, thank you. Sorry, Amartya and Zurab, over to you.
Thank you very much, Francesco. It's a great honor to have received this invitation from you to give the mini-school. We very much look forward, especially to the interactions that may arise through the discussions we will have. We try to make it as informal as possible, and if anyone at any stage wants to ask a question, please do so through the chat. And then maybe we can have at some point a little break where we answer questions before we continue further. I hand over to Amartya.
Thank you, Zurab. Thank you, Francesco. It's really a great honor for us for these invitations, and we very much hope that those who are attending this mini-school will enjoy it. And we are trying to make it in an informal way to present this category theory. And as we mentioned in our abstract, that the idea is to give an overview of this category theory without assuming anything knowing about category theory. And even for the first lecture, or rather today's lectures, we'll start from numbers and see how we can proceed from here. So our mode of presentations is little bit possibly is new, something that Zurab and I will actually discuss topics here, and we will both write on this whiteboard box. And you are most welcome also to ask your questions or queries or any kind of doubts, anything. And during our discussions, we will try to explain these concepts and also provide examples on that. Okay, Zurab, so we are ready to start then.
I think we are, yes. Thank you, Amartya. So let's look at what we have on menu here. I hope everybody can see the screen. Could you please explain this, Amartya?
Okay, so today is the first lecture. So day one, as we go to the restaurant, we get a menu card. So in today's menu card, we will try to do the following two things. One is the definition of a category. So our hope is that when we will finish our lecture today, at least you will get an idea to check whether certain things forms a category or not. And of course, you will get lots of examples from different contexts, mathematics or outside mathematics as well. And once again, please interrupt us if something is not clear or you need more clarification, because the idea is just to make it as informal as possible, but it's effective in the sense that the notion to make it clear as much possible. Thank you, Zurab.
In category theory, one kind of starts with the notion of a category. And we looked through quite a large number of available videos on the internet about category theory, and all of them are quite good. But somehow they always start with something else and trying to motivate the idea, and sometimes never even arriving to the definition of a category. So I suggest, Amartya, that we actually kind of do it the other way around. Why don't we begin defining what a category is? And then through the examples, maybe we can get a bit of motivation as well and a deeper insight. Can I maybe ask you, Amartya, to explain to me what is a directed graph?
As far as I know, in directed graphs, probably we have two things generally comes. One, something they need something called the yes. Can you see? Can you see now?
Oh yes, I can see now. Yes.
Yeah. So we have two kinds of things there in directed graphs. One is called the vertices. We draw the vertices here and there, and then we draw arrow between them. So like this, like this. But do you think that we can use this very simple idea of a directed graph to really get the idea of a category?
I think so, because, before we do that, actually, I want to add one more remark to what you said. Actually, not a remark, but a piece of drawing. I want to put this thing that you drew, kind of enclose it into a certain region like this, so that although a directed graph consists of a number of these vertices that you called and the arrows between them, we want to think of it as one thing. And so we have here one directed graph, and we could have another directed graph. I'm going to draw the arrows slightly differently, if you don't mind. And so each of these are separately directed graphs. And of course, we could put them together to form one big directed graph, but we're not going to do that. We want to showcase here the fact that we can have several different directed graphs. And the number of vertices in a directed graph or the number of edges is different depending on which directed graph we're looking at. And so there are many properties that would differ across the directed graphs. But one other thing I would add here, a kind of slight generalization, if we want to move towards the notion of a category, is that we want to consider directed graphs where we're also allowed to have arrows going in loops.
Okay, so let me add it also.
Yeah, and also possibly having multiple arrows between given vertices, and possibly in different directions.
Okay, so we have quite a good flexibility with drawing the graphs, which is indeed a very good thing.
Yeah, so that's what our directed graphs will be. They will be just these collections of vertices together with the data of arrows going back and forth between the vertices. And that all of that mathematical structure, as we call it in mathematics, constitutes a directed graph. And now we're very close to defining what a category is. But maybe before we do that, let's give some meaningful example of a directed graph from the knowledge that everybody already has. And I was thinking of him, you mentioned at the beginning something about numbers, and I was thinking about those numbers. So with numbers, we can form all sorts of directed graphs, and one of them would be a directed graph where vertices are numbers. Let's say we look at positive natural numbers 1, 2, 3, 4, 5, 6, and so on. So we can imagine that we've drawn all the numbers there, or maybe we just limit to maybe 7 numbers.
Yes, yes.
And the idea is that the edges we want to draw here are supposed to represent something meaningful, so that when we look at that graph, it could show us something about the object of interest. And in this
then
case,
we can actually, then we can, which comes to my mind naturally, ordering could be a very nice way to represent arrow.
Well, that's a good idea. We can have an arrow as soon as we have x being less or equal to y.
Yeah, yes.
Another way of drawing arrows, which would give us a different directed graph from the one you're suggesting, would be the divisibility relation. So when x divides y, in other words, when y is divisible by x. So for example, 2 would be divisible, 6 would divide, 2 would divide 6.
Yeah,
6
2
is divisible by 2.
Yeah.
But 5 does not divide 6. So 6 is not divisible by 5. So we will have an arrow going from 2 to 6. But we're not going to have an arrow going from 5 to 6. So maybe can you help me for us to kind of fill this diagram up with all the arrows
with respect to
relationships? Yes.
With this divisibility, right?
That's right. Yes.
So 1 is actually playing an interesting special character because we will always have an arrow from 1 to everybody else.
That's a good remark indeed. Yes.
And we need one more. Oh, sorry. I think.
We were doing the same thing there. Huh?
Yeah. No, it's fine. Yes, it's done actually.
Are we done?
Probably 3 to 6. Yes.
Well, if anyone in the audience notices that we missed some,
yes, please
do let us know. Okay.
So we are working with this one. Yeah.
I think we actually missed quite a bunch of arrows, to be honest. We missed all the looping arrows, didn't we? Because
but we first yes, every number divides itself.
Yes.
Oh, sorry.
Sorry, I took over all of those. So here is an example of a directed graph. Its vertices are some objects we're familiar with, and the arrows represent some relationship between the vertices. Now, there's one thing that's interesting about this directed graph. If we have an arrow from one vertex to another, let's say we choose an arrow from going from 1 to 2. So we have an arrow going from 1 to 2. Let me draw this separately. Right? And we also have an arrow going from 2 to 6.
Yes.
And that produces actually an arrow going from 1 to 6 as well.
Yes, I think from our childhood we know that if 1 divides 2 and 2 divides 6, then it implies 1 divides 6, right?
Yes, indeed. And it's a general phenomenon. It's not just for 1, 2, and 6, of course. It works for arbitrary numbers, that if A has an arrow going to B and B has an arrow going to C, then A will have an arrow going to C as well. And that
so
will
we can
work not
exploit
just
this
for
property.
Yeah.
We can exploit this property.
I think that will work also for your the directed graph that you wanted to create. The one.
Okay, the other one. Yeah.
Do you agree with that?
Yes, definitely, because we have the same kind of relation between these two types of. Yes.
It certainly doesn't work for this one.
No, it will not work, Gary. You are right.
We have, for example, we have an arrow. Let's actually label these with numbers as well. So in this directed graph, we have an arrow going from 1 to 2. We have an arrow going to from 2 to 3 as well, but we have nothing going from 1 to 3. So that rule fails there. And does it fail in the other one that the first one that you had there?
I think it also fails. Yes, for example, from here to here we have an arrow,
Right.
From here to here, we have an arrow, but we do not have an arrow here from here to here.
That's
so
right.
This is missing.
Yes.
So this is some kind of composition happening in general. Can we say like that?
When you say composition, that reminds me of functions between sets.
Yes.
Let me move down to explain what I mean. So if we have a set, for example, let's consider the set of real numbers, which in mathematics one denotes it like this, right? The bold, the thick R.
Yes.
We could consider the function that assigns to every number that number plus 2. This would be a function from the set of real numbers to the set of real numbers. And when I say from the set of real numbers to the set of real numbers, is that clear what I mean? I actually want to draw this function as an arrow. So the function takes an input value and has an output value, and so the input value comes from this set here, and this is the set where the output values lie. And then if I had another function going from again from the set of real numbers to itself, G. I'm thinking now these arrows should have actually been loops, right? Because they go from one thing to the same thing. I should have maybe drawn it like this.
Then
F
it will
going
be
like
easier
that
to
and
yes.
G going like that as well. But I think for clarity of what I'm going to explain afterwards, maybe it's better to keep the other notation. So let's consider the function. Oh,
okay.
Do you want to suggest what G should be?
Maybe e to the power x.
E to the power x. Okay. Yeah.
Yeah.
So when you said that composition, that kind of reminded me of the idea that we can compose functions.
Yes.
So we could now do the following. We could take G of f of x, and that will be a new function which we can call h of x.
Yes.
And we can actually see in this example what h of x will equal to. So let's figure out what is h of x. I forgot how to do that. Do you remember?
Yes. So we can write G and then plug in this value of f of x.
Okay.
And then we plug in the value of, in place of x, we write x plus 2, right?
Right. Okay, that makes sense. So we get an entirely new function, right? Something that is quite different from the original two. And then it kind of fits into the same picture. We have two arrows, one succeeding the other, and out of that we produce a third arrow. Just like in the other case, if I move down to the previous screen, we had here this idea that 1 divides 2, 2 divides 6. So 1 divides 2, and then we had 2 divides 6, and that was giving us an arrow from 1 to 6.
Yes.
And so in a similar way here, we have an arrow, which now is something very different from divisibility. This is now a function between sets. We have an arrow f, and we have an arrow G, and that gives us an arrow going all the way from where the first f was coming out from to where the G is going into, right?
So basically what is happening, whether we are talking in terms of functions or in terms of less than equal to relation or in terms of divisibility, all those have this common property.
That's right. And that common property, I wouldn't actually call it a property. I would even call it a structure, because it's kind of up to us to decide how we define H based on F and G. I mean, we can compose F and G, but we could also do all sorts of other things to F and G to get new function H. So it's part of the information we want our directed graph to be equipped with. The information of composing arrows when the arrows are arranged in the correct way. So let's explain this a bit more abstractly to see the bigger picture here. So imagine we start out with a directed graph as before, which has vertices and these arrows, the directed edges between them. but now we remember that there could be multiple arrows.
Yes.
Which actually doesn't work in our first example. We didn't really have a chance for multiple arrows there between two given objects, because I mean either one divides 4 or it doesn't divide 4, right? So we only have one arrow. But in this case, we certainly have multiple arrows between objects, because here we have one arrow, which is one function f that goes in a loop from R to R. And we have another arrow, G, which also goes in the loop from the same object to itself. The consideration of functions allows us to see the kind of value of allowing there to be multiple arrows between vertices. And so we now have this directed graph with all the arrows going between the vertices. And what we want is to have a bit more information, where we're also given, in addition to being given the data of all the vertices and the data of all the arrows, we're also given the data of how these arrows compose to give new arrows. So whenever I'm given f, an arrow from x to y, and I'm given an arrow g from y to z, I need to know what is their composite. It's for me to choose. There could be multiple different arrows from x to z, and I'll have to make a choice. And whatever choice I make, I'm going to represent it in a way that really reminds us of how sometimes one writes composition of functions, G circle F. So that's a choice I make.
So the idea is that yes, absolutely. If we two arrows are given such that the final destination of the first arrow is the same as the initial destination of the second arrow, then the third arrow should be given, which will be constituted by these given two arrows.
That's right, yeah. But this must be given to us for any single pair of arrows that match in the way that you described, that F goes into the vertex where G goes out from.
Yes.
So we will have a large table of information of which two arrows in the composite gives rise to the third arrow. Oops,
then probably in our picture we need to add some more arrows in this graph, because we have an arrow here, we have arrow here, but we should have an arrow here.
Yeah, we'll have to add a lot of arrows there. Yes,
lots of arrows we need to add.
That's right. So maybe we look at something simpler.
Yes, maybe.
Let's look at something very simple.
Just two vertices and one edge. Maybe that's one of the simplest.
Okay, so let's consider a directed graph with two vertices and one edge between them.
And then we need to add something within it.
Yeah, we need. We also need those ones, the looping arrows, or not, right? We didn't say anything about them yet. We're just looking at composition for now. And so we're actually kind of almost very close now to formulating the definition of a category. So a category will be a directed graph with possibility of multiple arrows between given objects, together with this data of compositions. And then some properties need to hold for that composition. Some rules need to be satisfied in order for this thing to be a category. But the good thing is that those rules, which we will formulate in a moment, will be all such that the examples we've given before, the examples of scenarios where given two arrows like that, we were able to create an arrow going from the first object to the last object. All of those will actually turn out to be examples of a category. But I'm wondering if we are ready or not yet to formulate the what those rules are. I also see there is a question from someone.
Okay, let's see the question.
Francesco, could you please maybe help us, Aurelia, to
okay, yes.
Look at the question.
The question is from Jean Duplessis, and the question is, if transitivity is forced, isn't it fine to just consider the transitive reduction of the directed graph?
Yes, when we are only interested in a situation where the choice of the composite is forced, like in situations like this, where we didn't have any choice. I mean, the arrow of going from 1 to 2, composed with the arrow going from 2 to 4, would give rise to arrow going from 1 to 4, and there were not many arrows to choose from. There was just one to name, and the one that's already there. So in those cases, then it will be fine indeed. But in the more general situation, when there are possibly many arrows going between objects, like for example here, there are many functions going from R to R, and so now the question is which of them is the composite of f and g? And so we have to now name which will be, because there are many of them. I hope that answers the question. Do we have any other questions as well, Ilya?
Probably not.
There is a raised arm, and I'm just letting the Tepang chance to ask his question. Tepang, you're welcome to unmute yourself and ask your question. Okay, the person just put down his arm. Probably that was by mistake. Okay, you can continue.
Okay, no problem.
Okay, so where were we? We were talking about a simple example. So we drew a directed graph with, let's call these vertices 1 and 2, and let's call the arrows 3, 4, and 5. And let's now, well, in this case, we don't have much choice, I guess. So to allow some choice, let's add another arrow here, which will be called 6. And now we have to decide how to define composition of arrows. Just to illustrate this idea that we have to give full information about the arrows, about the composition of arrows. So shall we do this in a kind of a table, Amartya?
Yes, that we can do. But do you want any special privilege should be given by these loops, or they will have the equal right compared to 4 and 5?
Not yet.
Not yet.
So right. Let's make a kind of multiplication table. So we will be composing the arrows with each other, and there are 1, 2, 3, 4 arrows. So let's index the rows with the tables.
I think Zurab, I think our vertex leveling and the edge leveling are, we want the same.
What do you mean?
Because we labeled the vertex as 1 and then also the arrow as the same numbers.
Yeah, and I'm getting confused now between those things. So maybe
you write U and V.
That's a good idea. Thank you very much.
Yes, for the
vertices. Objects are labeled by letters, and the arrows are labeled by these numbers. So 3, 4, 5, and 6. And we now want to describe what compositions are, but not any two will compose, right? Only those will compose that are matching. So let's figure out which are the matching ones, so we know which cells do we need to complete here. 3 matches with 3. Do you agree?
3 matches with 3. 3 matches with 4.
Okay.
3 matches. 3 dozen matches with 5.
3 matches with 6.
3 matches with 6. Yes, no, but not 5.
So 3 goes. It's like if we put in the place of F we put 3, then in the place of G we put 6. Then they match in the sense that the object to which 3 goes is the object from which 6 comes out, right?
Yes.
But the same is not true if we, for example, put in the place of G we put 5. Then it's not true that 3 goes into the object where G comes out, because 3 goes into the object U, and 5 comes out from the object V.
Right.
Okay, so let's continue. Shall we? Let's continue deciding what matches with what. So 4 does not match with 3.
So one immediate observation, probably one immediate observation is that everybody matches with itself.
Oh, okay, that makes sense.
Right? Because
Yes.
we can, like what we do in matrices, look the diagonal.
Yeah, I'm just erasing your text because I want to make them small so we can insert the composite values there as well. Okay, so what else does 4 match with? With 5 it does.
4 match with 5, yes, does.
With 6 it doesn't, and then 5 matches only with 5, and 6 matches with
only with 5.
as well.
Yes, yes.
Yeah. So these are the cells in which we'll have to put values that will be the composites of those arrows. And now we are free to decide whatever we want. So let's just put some random values there, except that the composite must fit this picture. So it must come out, the arrow must come out from where the F comes out, and it must go into where G goes into, right? So for 3 composed with 3, we'll have to have an arrow. Well, let's draw this. So 3 comes out from U and goes into U, and so if I want to compose 3 with itself, it will have to be an arrow going from U to U. And I notice now that a participant has indicated to us that 6 does not match with 6, and also that 4 does not match with 4, which is
true.
Absolutely right.
True. Absolutely.
Amartya, you very much misled me here.
Yes.
Right? You said everything matches with itself, but it's not true, huh?
Absolutely not true. Definitely.
So we're very embarrassed now.
Yes. Good.
Okay, but thank you very much for the input.
Thank you.
Okay, so 3 composed with 3 will have to be an arrow going from U to U, and there is only one such arrow, right? Because the only arrow from U to U is 3. So we are kind of forced to make this choice for this composite to be 3. And now 3 with 4, there we have 2 choices. Well, let's draw a diagram for 3 and 4. So 3 goes from U to U, and 4 goes from U to V, right? And so their composite could be either, so the composite has to go from U to V, so it could be either 4 or 6, right?
4 or 6, yes. So we have only 2 choices, yes.
Yeah, and so let's just make a random choice. So 3 composed with 4. You want to choose?
Yeah, let's choose 6.
Let's choose 6. 3 composed with 6. Let's choose that to be 4 for the sake of balance. 4 composed with 5. Let's choose that to be that has to be an arrow going from U to V. So maybe we can choose that to be 4 as well.
4 as well. Yes.
And what about 5 composed with 5, Amartya?
5 composed with 5. Do you have a choice? I think it's only 5.
Yeah, you're actually right. Yeah.
We don't have choices.
And what about 6 composed with 5?
6 composed with 5. It can be 6 or 4.
It could be either of the 2. Yes. Which one shall we choose? Maybe we can
Let's choose 4.
Which
yes, maybe we can choose.
Please tell us which to choose. 6 composed with 5. Should it be 6 or should it be 4? First answer that will come through, that's the choice we'll make.
6.
Okay, we have 6. So let's
okay, let's choose that. Yeah.
All right. So what we've done now, we've equipped this directed graph with an additional data, with a thing called composition. And we've specified that composition through this table. And now we can define what a category is. So do you want to have a go, or should I?
Yeah, please.
So a category is a directed graph together with this data of composition, which has to be fully specified, exactly what composed with what gives what, like we did in this example. But we can't just have an arbitrary table here. We need to have a composition that fulfills certain rules, certain axioms. So let's specify what these axioms are. There are 2 axioms, and they're quite easy axioms. We will then have fun checking whether the thing we constructed here will actually be a category or not, whether those axioms will hold or not. Okay, so let's go to another screen where we describe what these axioms are. So in a category, when we have arbitrary three arrows,
Zurab, I think,
in the following way.
sorry, Zurab, I think there is a question. Why do we need to add 6?
Isn't it 4 enough? For example, then 3 and 4 composition would be 4 again without ambiguity.
Can I also have a look at the wording of the question so to understand it better?
Yeah, you just need to click on Q&A
to add 6. Yeah, if you click on Q&A.
Yeah, if we want to if we want to expel 6 from our directed graph, we could do that.
Yes,
we could do that. There's not, but we will just get a different directed graph that way. We could actually throw out everything. We could just have nothing in the category. We can have a structure which has no vertices, no arrows, nothing at all. Then that would be a perfectly well-formed category. The idea is that in nature, you can't always discard everything. You need to sometimes consider various different things. And this is just an example illustrating that if we had to consider both 4 and 6, if they had some relevance to the problem we're working at, it might be so that the composite would have to be, in one case, one, and in the other case, the other. So it's not about trying to build an optimal directed graph, which could be just empty graph having no data or vertices or arrows. It's more taking a directed graph that's in need to be explored, and then seeing how composition can be defined on this directed graph, which says something meaningful about the underlying problem or underlying subject.
Yeah,
okay.
And just to add you that after mentioning these two axioms, what you said to need to be satisfied, maybe all our effort of the choices need to be changed again. That can also happen.
Well, I mean, what's wrong with something not being a category? I don't see anything wrong with that. The
Yes.
counterexample is just as useful as an example.
As an example,
So.
okay? Yes, let's go.
So let me go back to formulating the requirements, the axioms on a category. So if we have 3 objects arranged like this, F, G, and H. So my choice of letters X, Y, Z, and T is deliberate reference to physics. X, Y, Z is the 3 coordinates of our 3-dimensional world, and T is the time coordinate. It's typical in mathematics to use X, Y, Z, and after that T because of that origin. Okay, so if we have 3 arrows here, which are arranged like this, so F goes into where G goes out from, and G goes into where H goes out from, then we can do all sorts of things. We could compose G and F first, right?
Yeah.
And also maybe we should remark here that when we compose 2 things, the order in which this appears is different from the order in which F and G appear on the diagram.
G appears.
There is a reason for that, which I'm going to we can discuss it afterwards. So we could compose these 2, right?
Yeah.
And we could also do that, exactly. And now once we've done that, which is something we can do because remember we said that in our data of directed graph, we need to be given all these composites. Then the other thing we could consider here would be taking this result of composing G and F and then further composing that with H, which would then give H composed with G composed with F. Or alternatively,
we can use the other one. Yeah.
We could. Are you going to draw that, or should I draw that?
Yeah. Yeah.
Right.
And then we can put first H and G and then do F as it appears on the picture.
So I mean, there is no reason why these 2 arrows need, I mean, the one at the very top and the one at the very bottom, there's no reason why they need to be equal to each other.
Yes, yes.
But in a category, we require them to be equal. So every time we're given F, G, and H, we want these 2 arrows that we get as a result of the composites we just drew here to be equal to each other. And this is called law of associativity of composition.
Sure.
And I think we are making a mistake again, Amartya. This should have been on the diagram. Something is wrong.
It should be other way around.
Fixing it. This should have been H composed with G. Thank you very much.
Thank you.
Partha, for all the corrections. It should have been like that, because we in a composite we write on the left side the thing that was
you
done
told
once.
us. Yes.
Yeah.
You told us that how we write in the diagram and how we write for the composition is actually other way around.
Exactly.
So these need to be corrected as well.
That's right. Yeah.
Perfect.
And this is not showing on the screen, so let me fix it a bit like that. So that's one axiom of a category, that whenever we have arrows arranged in a way that's drawn in the picture here, these triple composites we can form in different order, they actually must match with each other. And the other axiom, so this is one axiom, and the other axiom is, I think you're a bit off screen, Amartya. What you write is goes right to the right and right, and then I'm chasing this one.
Go in this side. Yes.
The idea is not to go outside those blue boundaries.
Blue boundaries. Yes.
These ones.
Okay. Right. So this is our axiom.
So the other axiom says that for every object X, there must always be a special arrow that loops into X, which we call identity X. So this must exist for every X, and it needs to have the following property. I mean, there could be also other looping arrows. Okay, I don't care about the other arrows. All I'm saying here is that there must be one that's chosen, and that chosen one needs to have the following property, that if I compose that chosen one with an F or with a G, and now my F and G are a bit different from what they were before. Maybe I use a different letter here, E. So when I compose that identity with E, some arrow going into X, that result must always equal E. And when I compose identity with F, that result must always equal
always
F.
on the other side.
Yeah. And I don't know about you, but I can't help mentioning this example now, that we could have considered a category where there is only one object in the category. So let me draw a picture. There's only one object. We don't even have to give a name to that vertex. Object and vertex are synonyms to each other. And the arrows from that vertex to itself are the numbers 1, 2, 3, and there are as many arrows as there are numbers. And in that category, we could define, I mean, it's not a category yet because we haven't defined composition, but we could define composition like this. We could say, and now these arrows will be numbers, so let me use more familiar notation for numbers. So A composed with B, we could define that to be A times B, the usual multiplication of numbers.
Okay, so multiplication can be also thought as an arrow.
Not as an arrow, as a composition of arrows.
Okay, so it can be used to define the composition.
That's right, yes.
Right.
So we have one object in this directed graph. All the arrows are just the numbers, and the rule of composition is the rule of multiplication. And then, of course, everyone will agree that in this setup, we will have this associativity. This is a law that we learn at school, right?
Yes.
And now the question is, which will be this special arrow that will serve that purpose, that number multiplied by any other number gives us back that other number, and it doesn't matter in which order we multiply.
So that's actually very interesting thing what we learned from the school, that when you multiply any number by 1, it gives back that number.
Right. So you think that special arrow will be number 1?
Yes, maybe it will be because
Yeah, I think I agree with that indeed, because 1 times anything is that thing back. In fact,
so can we do this?
Here,
yeah. Can we do the similar way addition?
Well, that's an interesting question. Maybe this is something that our listeners would like to explore
Themselves,
before the next lecture as a kind of exercise.
Yes.
Shall we go back to the example that we had before and test whether the thing we created there is a category or not?
Yeah, you mean the table?
That's right. Yes.
Yeah.
So this little directed graph we had there, together with the composition defined according to that table. So let's make a little kind of a competition.
Yes.
So it's a competition. It's not really competition. I mean, let's ask the audience to identify a reason why this thing. Well, I actually don't think it will be. I mean, it's unlikely. We basically put these random numbers randomly. Why would it be?
Yes.
So who can identify first what is the problem? Why does this thing fail to be a category? So if you would like to post it in the chat, that would be we'll be very honored for that. So that would be a nice contribution from the audience. You can tell us if you can see why this thing does not fulfill one or the other axiom.
Okay, composition doesn't exist between all arrows.
Did we miss something here?
Oh, didn't we draw enough arrows so that the composition are all there?
We were doing those ticks to make sure that all composites are defined. So
yes, maybe anyone can help us. Which one is missing?
Yeah, if we missed something, then please prove your suggestion, Sumaya, if you think that we missed defining certain composite here. Otherwise, maybe others could give it a try to identify a reason why this thing isn't a category.
So we need to check whether this table satisfies those 2 axioms. That's what we wrote. And also, of course, what Sumaya said, that even if we forgot to add more arrows, which need to be 3 composed with 5. 3 composed with 5. How can we compose 3 with 5?
No, we cannot compose 3 with 5. So
because,
we can't because 3 is a looping arrow. It goes from U to U, and 5 goes from V to V. And in order to have the composite defined, we need to have the arrow going into the position from which the other arrow comes out. And we don't have that scenario here.
So probably, Sumaya, is it clear that why 3 cannot be composed 5 with respect to what Zurab mentioned about this composition law? In the meantime, part 2 also include find out a mistake. I mean, something shortage to not become a category is saying that identity fails at 3. Okay.
Right.
So for 3, there is a problem.
So that's a good point. So we wanted to have this special arrow. So let's explain this a bit more. We wanted to have this special arrow that has this feature that it's composite with anything else equals that thing back.
Yes.
And if we look at in this example that we were building up here, the question is what will be the special arrow for the object U? Because every object needs to have such a special arrow. And the only arrow we have from U to itself is the arrow 3. And that fails to be special because if it was special, 4 composed with 3 should have been equal to 4. And also 6 composed with 3 should have been equal to 6, because that's what being special means.
The axiom is, yes.
And if we look at this entry in the table, we can see that the composite of 3 and 4 is actually equal to 6 and not 4, which is what it should have been.
Sorry, Zurab, I think Martin also saying something which I couldn't understand. Martin, maybe you'd like to tell us ambiguity avoidance axiom. Although I didn't write the other one as axiom 2, maybe that we should do that, but maybe you wanted to mean something else. So there is some mistake, or axiom 2. Okay, thank you, Zurab. Okay, Martin looks like he's not here.
We have another reason why this thing fails to be a category. It just came through from.
Sorry, Martin. You're welcome to say it more, kind of to explain your comment. Martin, are you here?
So while Martin is sorting out the electronics, I guess, to connect with voice, let me mention this other counterexample that was pointed out. So let's explain why do these things do not equal. They must be equal because of that associativity axiom.
Yes, that's Piyush actually mentioned a very good point that it fails the first axiom.
Yeah, although I think there is a little bit of a problem here in terms of ordering things, because if these two sides of the equality were legitimately considerable, then the arrows would have to be arranged like this. 4 goes into where 3 comes out from, and 3 goes into where 5 comes out from. And if we look at the picture, that's not what's happening. It's actually the other way around. 3 goes, and then 4, and then 5. So the order of these has to be changed around. So it has to be 3 first, and then 4. And so I'm going to slightly modify this counterexample then, and maybe it will still be a counterexample. So let's put 4 there instead of 3 here, 4 and 3. And now we can check what is left-hand side equal to and what is right-hand side equal to, and see indeed if they're different from each other. So 3 composed with 4, I'm going to first evaluate the expression inside here, right?
Yes, so first 3 and then 4. So it should be 4.
So, no.
No, we don't have 4, we have 6, yes.
Yeah,
we have
according
6.
to this line, it's 6. So on the left side, we have 5 composed with 6, and that further equals... so it's 6 first and then 5, and that's equals
sorry,
6.
There is a question in the chat. For category theory to exist, does composition have to exist for all the errors?
Yes, I will come back to that question just now. Let me just finish this calculation. Thank you very much, Ilya. We'll come back to the question now. So on the left side, we get this equal to 6. And on the right side, let's evaluate now 5 composed with 4. So that's doing 4 first and then 5. So on the table, it gives us 4. And so this is 4 composed with 3. And that's 3 first and then 4. And so this is also equal to 6. So we're kind of lucky that in this specific example that was proposed as a counterexample, it actually isn't a counterexample. We do have, in this specific case of 3, 4, and 5, the left-hand side here and the right-hand side here equal as required by the associativity law. But we should be careful. It doesn't mean that the associativity law holds, because this law must hold for all possible errors, right? And here we just checked that it holds for one specific choice of F, G, and H, for 5, 4, and 3. We didn't check yet whether it holds for all the others as well or not. But we actually don't need to, because we already have a
counterexample, but Cardinal said 3 composed 3 composed 6. 3, 3, 6.
Okay, let's have a quick look at that. So 3 composed with 3 composed with 6. And I think 6. Again, the ordering needs to be adjusted a little bit, because 6, remember the ordering and the composition should be the other way around. So I'm going to reverse both sides. So it's 6 composed with 3 composed with 3. And let's see if that equals or not to 6 composed with 3, and that composed with 3.
So 3 composed 3, what did you write? 3?
3 composed with 3 is equal to 3. So the left-hand side is 6 composed with 3.
Right. And 6 composed with 3.
That's 4, right?
That's 4. And 6
side,
composed with 3. 4 composed 3.
And that equals 6.
Yes.
So they're indeed different. So that's a good one.
Thank you, Gordon.
Yeah, thank you indeed. So not just we now saw that not just the identity law, I mean the second axiom, not just the second axiom fails, in this example we had before,
yes,
but also the first one does.
yes.
So both of them fail. However, we of course didn't need to know that both of them fail. As soon as one of them fail, we already don't have a category.
Right.
And now this brings us to the question, okay, but when do these axioms actually hold, right? And I mean, the examples we kind of sketched in the beginning, it will turn out they hold in all of them. But this also brings us to the end of this hour. So I think we have to leave considering situations where the axioms do hold for the next time.
Yes, yes. Let us stop here. Okay, thank you.
Okay,
Yeah,
and there are.
Sorry.
There is, I mean, like you might consider answering the question about the for
Ilya,
category
thank you
to
for
exist.
reminding me that.
And there is one more. There is how to say the explanation of the question by Martin, who probably have difficulties with his mic. So I meant one cannot have the same arrow with more than one pair of the source and target. So when he was previously saying ambiguity avoidance axiom.
Yes, that's a good point. Thank you very much for that remark and question. Indeed, each arrow can only have one source and one target.
Yes, absolutely.
Like we were trying to show in all the pictures. So an arrow needs to remember what its source is and needs to remember what its target is. It cannot have two thoughts about that. And Ilya, what was this other question?
The other one was, for a category to exist, does composition have to exist between all the arrows?
That's a very good question as well.
As long as we satisfy that picture.
So not all the arrows, only those ones where the two arrows are such that the F goes into an object from which G goes out. So only for such pairs of arrows, not all pairs, but only for such. And that's why we left some of the cells here blank, because these are the cells where the composite should not have been defined, because they only must be defined exactly in the situations that are described by this picture.
Okay, so to the best of what I can see, that is all the questions which were in the Q&A in chat.
Ilya, somebody raised their hand. Maybe you would like
Yes, I'm given the right to talk, yeah.
Yeah, thank you.
Hello, I just had a question with this graph here with the U and V nodes. Sorry, can you hear me?
Yes,
We can hear you.
Yes, so would I be correct to say that a composition of 3 and 4 would be 4 as well?
It's for us to decide, but if we want this to be a category, then yes, then it has to be 4.
Then yes. But if we do not want it to, yeah.
The point that is confusing me is that like if you say a composition of 3 and 4 is 4, but can also be 6, it's that how do we know that like 6 is a valid composition? Because if we take U and V to be sets, how do we know that the mapping is in the same order? Like an element of U maps to the same element of V for both 4 and 6.
Because to make it a category, it must satisfy these two axioms. And then in axiom 2, actually gives us no choice for 6, but only for 4, if we compose 4 with 3.
So Timerson, maybe it will also help to remark that in this picture, right, these arrows don't have to be functions. They could be anything. They could be numbers the way they are on the picture. They don't have to be something specific. But of course, we could have such a diagram for some specific situations, right? And in one specific situation, we might want to define the composite to be one thing, in another one, another thing. So just the picture does not tell us what the category is. The picture has to come together with the information of how the compositions are defined. So it has to come together with this table. And if you try to apply this diagram to a concrete situation where the table tells you that the composite of 3 and 4 is 6, but your specific situation tells you that it's not, that it should be something else, that it means that your specific situation is not an example of this general structure we built here. But we could also consider a general structure of which your situation would be an example by choosing a different composition. But in one category, we cannot have all sorts of different compositions. We have to make up our mind, get the table, and then make sure the axioms hold, and that will consider the category if the axioms do hold.
I see. So it's not like you're given the graph and then you can decide it's a category. It has to be defined as a category first before you can start applying that.
That's right. Yeah. So just being given a graph is not enough information. We also need to know what choices we made for compositions. So a graph doesn't know what composition is.
Thank you so much.
Thank you.
Thank you, Tim. Partha added a nice representation of these vertex arrows things in terms of machine and programs, which can be interpreted in the form of a category.
Yes, maybe I should mention here that we kind of completely skipped all the motivations and applications and all of that because your colloquium talk next Monday, Amartya, you will explain the links with various different subjects or category theory.
Yeah, if there are no more urgent questions, then it's as usual my very pleasant task to thank the two speakers, Amartya and Zurab, for this fantastic introduction to category theory in a completely new format that we never had before. That was really very entertaining. Thank you so much. And also thank you, Zurab, for already doing the advert for the colloquium that we will have on Monday. And we will make sure that all the participants receive the announcement on time, so that that can also be integral part of the course. Yeah. And as I mentioned at the very beginning, after the lecture is over, just in a few moments, we would like to invite you to join us in Kumo Space. And if you scroll back to the top of the chat, you find the link, or otherwise it should have opened automatically in your browser. And you just click on the room that is called NITheCS Social, yeah, so that we don't lose ourselves in the virtual space. Okay, then thank you very much. Amartya and Zurab, and thank you to all the participants. We will continue the course next week, Tuesday, at the same time, under the same Zoom link. And I hope to see you all there again next week, and to see you as well on Monday. So thank you very much.
Thank you very much.
Thank you very much. Thank you.
Please keep staying safe. Yeah, thank you.
Thank you.
Bye-bye.
Thank you, Francis.
We'll see you just now in Kumo Space.
Yes.
Sure. Thank you. Thank you.
Thank you.